to present Professor Vogel. Professor Vogel is a Professor Emeritus and Research Professor at the Department of Civil and Environmental Engineering at Tufts University since 2016, but he worked for the previous 33 years in Tufts University, where he was also the former director of the graduate program in Water System Science and Society. His research experience covers a really broad range of topics that includes hydrology, water resource and engineering, natural hazards, and in general, environmental statistics. It's important to stress that most of his research involves the application of stochastic approaches to the solution of applied problems in the field of hydrology and in the field of water resource engineering. And I want to mention reservoir operations, water supply, floods, droughts, water quality, and so on. Instead of going on listing his large experience in terms of knowledge in hydrology, but and most importantly in statistical hydrology, because it's the topic we are talking today, I want to recall that he was able to transfer his knowledge from hydrology to other fields of application that are related to natural hazards, that are earthquakes, landslide, sea level rise, and so on. And finally, I want to stress that when we asked to Professor Vogel to participate to the summer school, he was really enthusiastic for the idea of communicating his knowledge and experience, and especially for having the opportunity to share ideas and work together on the topic of extremes. So, given this, I want to leave the stage to Professor Vogel with great pleasure.
Thank you very much. Thank you very much, Elena. And let's see, do I have, whoops, is that, okay. Is everyone seeing my screen now and listening to me okay?
Yes.
Okay.
Perfectly.
Thank you, Elena, for that wonderful introduction. By the way, I didn't transfer my ideas to other fields. It's actually, I just like to make that clear. I transfer the knowledge, our knowledge. I feel hydrology, we have such an evolved field in the area of extremes that it makes sense to for us to think about transfer of our knowledge to other fields. More on that next summer. We can talk about that and why I believe that it goes back to perhaps Gumbel being a mathematician who helped, his first studies were only on floods and droughts. But more on that next year. So I am here, and thanks so much to the organizing committee and it really wonderful venue, really, that I look forward to next summer, all hopes. Okay. So what I'm going to do is a little different. I'm going to just throw out some ideas, try to express them as clearly as I can. And they all fall under this rubric of my title on the impact, identification, and treatment of extraordinary floods in the systematic record. So I'll need to define some of those things more clearly and what it is I'm really trying to accomplish. Let's begin just with a sort of an example, just to get your, rather than tell you what I'm going to tell you and so forth. What this is just a little glimpse of a way of thinking about what drives me here. I am driven often in the solution of, in developing research by ideas, by interesting ideas that I think everyone would agree we need to understand. So, what I'm going to talk about here are some ideas that possibly we could work together with as on the workshop setting or before and after that in collaborations. But here's the problem. Let me just generate a sample from a log normal distribution on the left side, a sample of size 100 with a coefficient of variation of 1 that, 10, an average of 10 cubic meters per second and a standard deviation of 10 cubic meters per second. And then what I did is I just generated 1,000 years, and I took the largest of those 1,000 years from the same log normal population, and I plotted it using that inverted
Richard,
red
sorry
triangle.
interrupting, Richard.
Yes.
I am seeing the first slide not in presenting mode. Maybe you have another screen different from what we're seeing.
Oh.
I still see the title.
Really? You're not seeing that now.
I'm seeing the yeah, but it's not in presenting mode, I think. Now I see the second. You switched to the second.
Is this the presenting mode? I'm sorry, block.
No, that's okay. You probably have too many screens.
No. I should be. I shouldn't have. I don't know. Oh, I have to change the display settings, I think.
So you're seeing presentation right now? Oh, okay. It's right there.
I don't know. So you're not seeing.
We're seeing the presenter mode now with the current.
How do I change that? How do I change that? Because I don't. That wasn't happening before.
Maybe display setting up there.
This is okay. Why not?
Yeah, this is fine, but it's just
It's fine, and you can
duplicate
just
slideshow, perhaps.
What?
Yay! Now it's perfect.
It is perfect. You sure?
Yes. Yes.
Yes.
Yes.
Okay, you're seeing. Okay. Okay. So.
Excellent.
All right. So what I did is I generated. Effectively, the sample on the right is 101 years of independent, identically distributed log normal data. And, you know, we could have easily been confronted with this. We would actually call just terminology that 1,000-year flood. You know, if we had that, now let's think about this as it's a 101-year record, systematic gauged record. That 1,000-year flood, I wouldn't know it was a 1,000-year flood if I was a hydrologist. We would call that the flood of record. It would be the largest flood in 101 years. And that's just, these are just terms. But the fact that it falls on, it actually falls somewhat of an outlier in the probability plot. Actually, those are approximate confidence intervals created by Minitab. There are exact confidence intervals for this case from a paper in 1981 by Jerry Stedinger. Those are not exact, but good enough. And I don't care so much about the confidence intervals. I want to know what to do with that triangle. Should I go to great lengths and find a distribution, perhaps one of the distributions that Simon introduced, to do a better job of having the fitted distribution pass through that? Or should I treat it separately? Should I do what Kirby said in 1970s? He said to just fit the sample with and without it and try to minimize the mean square error, take the average of those two results of the design events. I don't know what to do. I think it's an extremely important issue, and you'll see why as I talk about this more. So how do we deal with that situation? And it's not uncommon. It is not at all uncommon. Think about this. Probability of at least one 1,000-year flood in the next 100 years is about 1 in 10. So in every record of 100 years, there's a 1 in 10 chance that it contains a 1,000-year flood. Of course, we knew that it contains, very likely that it contained a 100-year flood, because the probability of at least one 100-year flood in 100 years is about 0.63. The point is that these remarkable or extraordinary floods may be remarkable and extraordinary in a given site, but when you look at the world in so many different possible places, it's no longer that extraordinary. So by the way, on the topic of the theory of that event, the record, the highest, the flood of record, I just wanted to point this out. I'm not going to go through this, but this book just came out. It's called Statistical Analysis of Hydrologic Variables. And inside there's a chapter where we actually derive the probability distribution of the flood of record for a whole host of different situations. It might be of some interest to you. And by the way, anything that has my name on it, you can download from my website. Otherwise, all the other references I give today are in the last slide of this presentation. So first, a bit of nomenclature. The systematic record is the one that we collected. In the right-hand slide, it would be those open circles. It's the gauged flow record. As you notice, at the top of that slide on the right, you'll see there's an extraordinary event there, June 16th. That's one event that occurred in '65, much bigger than all the others. Just clarifying that this right-hand side of the figure is the systematic record, whereas the left-hand side is what we often refer to. Often referred to as the historical record, which has to do with events observed by humans, usually non-hydrologists, in a non-systematic way. They really look like things like this picture here on the lower left, often just flood marks, elevation, discharge, flood marks. I am not going to talk about the historical record here. Today, I'm really just focusing on analysis of data based on the systematic record. Now, what is a spurious observation? Well, that's just what we think. It's a spurious result. It could have been a measurement error, could have been typographical. I'm not talking about spurious observations here. I'm talking about outliers. I'm talking about what do we do with what is now called potentially influential floods. Actually, in America, in our bulletin 17C, which I referenced below, the England et al. 2018 is a really good reference for everyone, anyone here, because what it does is it summarizes the United States approach. And I know we use a different distribution than elsewhere, but there are some very sophisticated and very impressive methods in that document. And they do deal with outliers, but they only deal with what are called PILFs, P-I-L-F, potentially influential low floods. Never do they mention what should we do with large ones. So I do think this is an area that just hasn't seen very much, given much attention. And even when you think about outlier tests, which I'm not going to talk about, they would benefit a great deal from that book I just showed you on the previous page. Remember this, you could use the theory in this chapter to develop outlier tests, which maybe someone wants to do here. Back to where I was. This is very important in a practical matter. This is a paper from looking at water surface elevations from storm surges in Dunkirk, France. The paper is the top row is blending of the systematic record with a single historic record, and you can see the fit on the right. And then as we go down to the bottom, we've increased the historic record, and we've even gone back and they've already gone back and looked at archival data. And what you do when you do all the statistics properly and include all those historical and archival records, you really can get quite a good understanding, which is very different. The lower right-hand graph probability plot is quite different from the upper one if one looks closely. And this is the sort of thing that it's hydrology, statistical hydrology at its best right here. But again, I'm ignoring the historical stuff. So now let's look at systematic records and what are we going to do about those large observations. First of all, we need to introduce a probability plot. There are two kinds. The most common kind are called quantile plots, or QQ plots. And those are, just as shown in the picture, a plot of the sample, quantiles based on the sample versus theoretical quantiles from the fitted distribution, whatever its distribution interests you. I feel like I hope, is everyone hearing me okay?
Yes.
Yes, we are.
I heard some things on my phone. I want to make sure it wasn't, okay, thank you.
Everything is okay.
Here. We're here.
A goodness of fit test that is actually quite powerful compared to other hypothesis tests is just by simply calculating the correlation between the two axes. We call that the probability plot correlation coefficient. you'll see today that it's extremely problematic, but it's very commonly used. So that's it's so easy to compute, and there are hypothesis state tests which have been derived on the basis of many distributions. So we know what the probability distribution of the probability plot correlation coefficient is for many just two-parameter distributions. It's a widely used test and quite useful. Let's try it out and show you what concerns the beginning of some of my concerns. So what here I'm looking at is a data set that was used by Bob Hirsch in Ryberg in a paper in which they attempted to evaluate the changes in floods that arise from changes in carbon dioxide levels. And so they wanted to use really long records. So they chose these 200 records. These are 200 USGS sites with records that go from 85 to 127 years, almost 100-year-long records. These are good records. First of all, an L moment diagram shows fairly clearly that that the GeV distribution, at least it would be hard to throw out. Can't say much more. Interestingly, on the right, if you look at box plots of the probability plot correlation coefficient for the GeV and for the log 3-parameter log normal and for the 3-parameter log Pearson, they all give incredibly good fits, especially when compared to the 2-parameter distributions. That's usually the case because they have an extra parameter. You'll see why that can be very misleading, actually, that 3rd parameter. And that's the subject of what I'm about to talk about. But what's interesting about that is take a look at what really was going on here. First of all, we identified what would be called the outliers, high outliers, big floods that were extraordinary, using a test by Grubbs in 1669. It's one of the most popular tests. Of course, it's for normal data. It's not for GeV data, but and so it is somewhat questioned. Again, we need outlier tests suited to our profession. That would be a nice thing for someone to work on with me next summer. The solid triangles are simply those events which were bigger than the fitted distribution with the 1,000-year flood from the fitted distribution. In other words, at each one of the 200 sites, we fit, in the case of GeV or Gumbel or so on, you fit the distribution to each of the 200 sites, and then ask the question, did any of those observations exceed the 1,000-year flood? And the answer is, yeah, a whole bunch of them did, and you can see them all, and they're always, look at what it looks like. Regardless of the model considered, samples with observations larger than the 1,000-year flood always had the very low PPCC values. In other words, it was that those extraordinary or those outliers or those largest floods that dominated, that really made it difficult for us to claim a good fit. They led to the worst fits, almost, and universally so. You barely see any of the really good fits, the ones at the top of the box plots, arising from samples that had very large, extraordinary floods. And we were wondering, is that really always the case, or is there some artifact here? So we did this experiment. We generated 10,000 samples, each of length of 100. That's a lot of samples. You would expect, we did it for the 3 cases here, and we plotted the probability plot using the true parameters. That's because we did an experiment. We know the true parameters, the 3 parameters of each of the 3 distributions. On the x-axis, we compute the PPCs based on sample estimates. And these were all using L moment estimators of the parameters. But what you see again is the same theme I just showed you, is that the goodness of fit is generally lower when you use the true parameters. In other words, if you actually knew the true parameters, you would tend to reject these distributions quicker than if you didn't. And so it's quite interesting that you didn't do better by knowing. In other words, the goodness of fit didn't increase as you would hope it would when you knew the true parameters. Rather, the goodness of fit actually decreased when you knew the true parameters. Now, this shouldn't be a surprise. The goodness of fit using the known or true parameters it shouldn't surprise us that fitting the true model degrades a goodness of fit, because goodness of fit is really misleading. I showed that a long time ago, back in 1991. I'm just going to point this out. This is really this was a very interesting experience for me. I was asked by the US government to develop a hypothesis test for the log Pearson type 3. And this paper at the bottom is the conclusion. In fact, I concluded that, no, you can't do this, and you better not, because it's very misleading. And why? What you see on the three figures here are, we're looking at the hypothesis test statistic. The probability plot correlation coefficient is a function of sample size and skew for the Pearson type 3 distribution. And what you notice, because the scale is the same on all three plots, is that the top one always has the highest, they look better. Why? The top one is method 1, where we estimated everything. We had to estimate the sample skew using a sample estimator, and we had to estimate the exceedance probability using Blum's plotting position. Whereas look at the bottom one, just forget the middle now, look at the bottom. We use the true skew and an unbiased plotting position, and it's very different. The fit of the distribution is very different. And the way I would like to summarize this is, you can think of the skewness, that third parameter, as just a knob that you really just turn to straighten out the data. It's very misleading. It's just a knob that you can turn to make you think you got a better fit, when in fact you don't. That's the fact, that you don't really. So how do we get around? Again, this is all caused by these large events. I'm just checking. I still have, according to my watch, I still have 23 minutes. Is that correct?
Yes, it is.
Well, I'm not going even close to that, but I just wanted to. So what we did to evaluate this a little bit more further, I just have shown you a few examples. Actually, what I've shown you so far is that the goodness of fit of a probability distribution can be very misleading using standard hypothesis tests. I'll show you. I can show you a way around that, which I can't wait now to talk about with some of you, particularly Grimaldi, who loves copulas, because a copula approach to this can get around all this. But we'll talk about that at the end. But in addition to the goodness of fit being misleading, another really important issue has to do with the shape parameter. And this is all so nice. I couldn't have asked for a better introduction from Simon and from Illyria. Simon, talked about the need for an extra shape parameter. Here I'm going to show you how difficult it would be, even with one shape parameter, how misleading things can be. And I'm not sure we'll get around all those problems with another shape parameter, but it's definitely worth trying. So here, what I noticed, we're just trying to figure this all out. Why is this really happening? Is it estimation? Does it have to do with parameter estimation? Does it have to do with the kind of hypothesis test? Well, here's another artifact that we found. First of all, when we fit the GeV distribution to those sites, and those sites are quite far apart, you could almost assume they're independent spatially, because our nation's so big and most of those sites are pretty far away from each other. So if they were independent spatially and in time, then in the 200 sites with all those records, there were 19,000 observations. So we should get about 19,000-year floods. And the confidence interval on that, using a binomial distribution, gives around, I should get somewhere between 12 and 26 1,000-year floods when I fit a distribution. Well, what I did is I fit the GeV using L moments, and I only got 6 1,000-year floods. Only 30% of the sites indicated 1,000-year floods. That's not as many as I expected. I should have gotten upwards of around 19. Why? There's a possibility that GeV exhibits some kind of bias. Why is this? Well, let's look at this. Here's the final experiment to talk about with you, and then I have many comments to discuss. So we'll look at this for as long as it takes to make sure you understand. Again, it was so helpful to have both Ilaria and Simon talk. Simon expressed the generalized extreme value distribution in terms of the shape parameter that's usually used, and so did Ilaria, that's usually used by statisticians, which I believe is what is the term for that Greek character? Eta, is it? Or no, it's not eta, it's, what is it?
Psi.
Psi, thank you. But in fact, Larry also showed us that in America or in many other places in hydrology, we use the term kappa. And one is the negative of the other. So in this case, a positive kappa leads to an upper bound, and negative kappa leads to a lower bound. So it's in other words, it leads to a distribution with a lower bound when kappa is negative as opposed to an upper bound when it's positive. And when kappa is 0, we have a Gumbel distribution. So first of all, what we did is we generated 10,000 samples of length 1,000. If you take 10,000 and multiply it by 1,000, that's how many sample years we had. So you'd expect 1,000. You would expect 1,000 events larger than a 1,000-year event. In this 10,000 samples of length 100, you would expect to get about 1,000 events, and that's shown by the line, the horizontal line, and that's actually a result you would hope for. And the only way we were able to get that is by fixing kappa at its known value. So we pretended we actually knew kappa because we did these experiments. But look what happens when we had to estimate kappa. And remember, these are 100-year samples. So this is all for a sample size of 100. And what you see in the other, when we had to estimate kappa, is that curve that goes, and what you see is that it almost never leads to 1,000. It's either a much more or much fewer. In fact, of interest is the bottom axis shows the range of kappa. The range of kappa that we found in those 200 sites that from the Hirsch and Ryberg data set, they're shown, you can see the range of those 200 stations. And what you see there is about 30% of the sites, just like you expected, 30% of the expected floods were in that vicinity. So yes, that's why it probably was happening, was because of the range of kappa. The point I'm trying to make here is it's all about kappa. It's not only all about it, it's all about your ability to estimate kappa. And the problem we found gets much bigger the closer you are to 0. There's some really interesting things that happen as you approach 0, as you'd expect, because that's the special case of GEV when it turns into a Gumbel. My point here is really, obvious that we knew that you need to have a good estimate. Now, how are you going to get a good estimate? It implies that probably the only way forward with using a GEV distribution in any reliable manner, unless you have thousands of years of data, which you don't. Here we have 100, we assumed 100, would be to use a regional analysis. And that is exactly what the literature talks about. If you read the literature closely, it turns out there was an evolution in our field back in the 80s and 90s that really showed very clearly that regional flood frequency is the way to go, and it's just absolutely essential. And you can see that that's probably the case here as well. Finally, if you wanted to get around that problem with the QQ plots and the probability plots, look what happens if I simply make my plots a little bit differently. Instead of making a quantile plot, which is what most people do and how most of the hypothesis tests using probability plots have been based on the technique on the left. Remember that plot? We showed it earlier, where we showed that the solid triangles were all those events which were bigger than 1,000-year flood in that Hirsch-Ryberg data set. Well, on the right, we simply made the plots differently. We used PP plots. In other words, we plotted the exceedance probability based on a plotting position versus the fitted exceedance probability from the fitted distribution, whatever the distribution was. And there you see a much more balanced view. You see, regardless of whether we saw an outlier or had a big flood, we still get those events are spaced as you would expect, uniformly about the box plots. So what that says is that I think we really ought to be no longer be using these QQ plots. We really should derive a suite of hypothesis tests based on the probability plot using PP plots. And that would, like I said earlier, that could benefit dramatically from knowledge of folks' copula, because that really is a copula. It's a PP probability plot is a copula. Well, in summary, I hope you'll agree goodness of fit can be misleading. I have other series of papers on this relating to rainfall runoff modeling. I'd love to share with some of that. Many of the same issues, you suffer from the same issues for different reasons. Fitted models tend to look better than the true model, and that is very misleading. One would hope it would be the other way around. Don't base decisions only on those on the QQ plots, unless instead try the PP plots. And we really need to think about reliable shape parameters, especially for drought, design drought and estimation. But the real moral here, I hope you take away, is that how we deal with those large outliers is critical. It's critical, and it hasn't received enough attention. And a whole range of issues I'm talking about here, from well, here are some examples, some papers that we could write together. And by the way, I'm very open about all this. I tend to like to throw out ideas and see who's going to really help me with some of this, because I don't do too many calculations these days. On the impact, identification, and treatment of extraordinary floods, that's what I spoke about. But perhaps some interest in developing PP probability plots and hypothesis tests. Perhaps even a paper on how misleading goodness of fit is, because it goes beyond the examples I gave you. I showed you some examples where it really is, but there are many other examples in other different areas of hydrologic engineering. And finally, improvements in estimation of the shape parameter for flood frequency analysis. Now, that's based on what I presented today. The way other topics that I plan on talking about with you next year, these are my 3 favorite topics right at the moment that I've been mostly, the topic I talked about today, I haven't been working on for many years, and it's based mostly on an unpublished PhD dissertation by Brent Bowler. And so most of what you saw today hasn't actually been published. But here are the ones I have been publishing on. I'm very interested in accounting for stochastic persistence and trends when updating flood and drought frequency. Ilarius talked about modeling the impact of trends and updating a flood frequency analysis. But what about stochastic persistence? Simon talked about that. The need for stochastic models which are representative of both marginal distributions as well as their stochastic persistence. Well, put it all together. We have the marginal distributions, we have stochastic persistence, and we have deterministic trends. And how do you do all that? This seems like a really nice venue for us to work with such brilliant colleagues that are working in those areas. One of my also favorite areas has always been the recurrence of the drought of record. Well, the drought of record is like the flood of record, it follows the theory of extremes. It's a little more complicated in some fashion because it's a cumulative process, unlike floods. So the drought of record is a cumulative sum, and so it's quite a different problem. And finally, perhaps my all-time favorite lately I've been publishing or writing mostly about is methods for generating stochastic ensembles of extreme events using deterministic simulation models. There is a tremendous need now to convert rainfall runoff models, deterministic simulation, rainfall runoff models, and the like, other kind, water quality, you name it, simulation models used widely in practice And there's a tremendous need for converting them to enable them to generate stochastic ensembles, which are representative, stochastic ensembles which are representative of the data that was used to calibrate and build those models. And that is absolutely essential for water planning, risk-based decision-making, and it's the future of our field. So those methods that Simon referred to, Simon is really on the forefront. You're very lucky to have him here. He's on the forefront of developing what I would call stochastic hydroclimatologic models. These are stochastic models. Primarily, they're rooted in the stochastic nature of the processes. But what I'm talking about here is a little different, but would benefit profoundly from his participation. I'm talking about converting deterministic models, which have all the stuff the engineers need because they explain how the parameters are affected by land use and how the parameters are affected by all the processes on the watersheding and how the inputs affect the outputs. And so they're the engineering tools of our future. We need to make them usable by generating stochastic ensembles. And that's the end of my talk. I just wanted to show you, here are a few of the papers I referred to during the talk. Thank you very much.
Thank you, Richard. Thank you very much for your wonderful presentation. I loved your presentation, especially the last slide and especially the last topic, the very last one. There is
Okay.
someone that wants to work with you on this topic. I say I'm
Okay.
available.
Well,
Okay, but I don't want to lose time because I know that there is someone who wants to ask a question or to make a quick comment. That obviously is Simon. So, please, Simon.
Thanks, Elena. Richard, amazing presentation. Just a comment that I can't help, and it was about this notation. Really, it's not of essence, but I really can't help it. Indeed, if somebody search the literature, it sees that for the same distribution, you have 1,000 different notation. I suppose based on the morning mood of the authors, Greek letters, English letters, A, B, C, D, or whatever. So I just want to say, I thought about this quite a lot 10 years ago, and I think I'm quite happy with the solution I found. Since we have only 3 types of parameters, that's it, 3. If it is if a distribution has a location parameter, I name it alpha. If it has a scale parameter, I name it beta. If it has a shape parameter, I name it gamma. If it has more than one of the same type, I add indices. So distributions that have 2 shape parameters, I make it gamma 1 and gamma 2. So I always know, just by seeing a distribution, what is the function of the parameter. So just I want to comment on that. I couldn't help it.
I like that. I like that.
Thank you, Simon. And there is another question from Marco. Marco, do you want to say something?
Yes, I'm here. Sorry, I needed to press the button. Thank you for the presentation, Richard. Really interesting. I enjoyed very much. You're pointing out the charter record being sometimes looking as an outlier, and how the kappa or psi or whatever being so important. Are these signs that in reality maybe we should go beyond, as also Simon has suggested, the traditional GEV, meaning this is bringing about all these problems because it is so sensitive to large values, and this K or Xi parameter is really hard to, I mean, if it even exists, it's hard to estimate. So do you have a comment on going beyond GEV?
Well, you asked the wrong person, but I'm going to give you the answer. Is speak with Simon. He just wrote a beautiful paper on this that really, well, I suspect it's whatever. Anyway, a paper will be coming out at some point that really speaks to potentially the need for one of those distributions he talked about for a whole variety of reasons he went through in the paper. Why the GEV distribution, although we always think of it. I always, before reading his paper, I always thought of GEV as the the theoretical distribution of choice because of its the theoretical asymptotic properties, which still hold, but perhaps not always in our field adequately enough because the numbers aren't big enough. We're not reaching the asymptotic limit, or even approximating, apparently. I don't know. I would ask that question to Simon. He has that's what I would do. I'm very hopeful that one of the Bird distributions, or if not the generalized gamma for the case of precipitation, and then the Bird distribution for some of the other cases, has tremendous promise.
And if I may add, I would like to make a modest proposal that is also in contention. There are other approaches that I think, focus more on the body of the distribution that I think would be a good option. And of course, I love Simon's work, and this all makes me resent COVID even more, because I can only imagine the nice conversations we'll be having tonight with some wine and with in the villa there, and that would be great. We'll have to wait. Thank you so much for answering.
Just a very quick comment on that. Let's see when the paper is published. We'll have time to discuss, but I agree with you, Richard, and with Mark also. There is a tendency to start exploring different things. Also with the work Mark and others do on metastatistical distributions, maybe there's some project that I'm trying to introduce also, but I do indeed feel that there is a need to try to explore more on this direction.
Yeah, I would, since you did ask me that, I would say, and I had been working recently on trying to mimic all the stochastic properties of daily flow. When we're talking, it depends on the signals. So for we have different problems. If we're talking about daily precip and stream flow, where you have the mixed processes, I do think that mixture models are really a very promising approach, because a mixture model can look, I mean, you can just mix two normal distributions and get the most unbelievably complex result. I mean, mixtures are beautiful. They're elegant. You can derive all the properties of a mixture. It's another area I'm surprised we haven't written enough of. I know there are many papers who have done some mixtures, but really it's not as, there's a lot of hope there, I think. Because our processes are mixtures. Certainly, if you take any deterministic signal within the rainfall or stream flow series, it's a mixture. It's a mixture of seasons.